各位老师、各位同学好，那我们今天就开始这个礼拜的量子资讯专题演讲然后我们很荣幸邀请到这个陈信良教授那陈信良教授是我们成大毕业的学长那他在我们成大拿到博士学位之后呢，就到这个德国做了这个博士后做了好几年了，曾经待过这个慕尼黑，还有待过柏林那他于今年2月到这个很荣幸的到这个中兴大学任教那他今天要给我们讲的题目是self-testing of steerable quantum assemblage 请信良开始
好，那谢谢陈元老师的介绍。那就是对，距离我上次回来的时候，大概是2年前，那时候在2020年回来台湾投票的时候。然后那时候没想到说，我回德国之后呢，下次回来居然要再隔2年之后才回得来，因为中间疫情的关系。那就是说回到台湾之后呢，然后因为下飞机隔离吧，然后马上就到中兴去任教，所以一直就是说中间很忙，一直没有机会回来。那陈老师问我，有没有机会来给演讲，然后当然就很开心的可以答应来，然后来这边给演讲。好，那虽然说这礼拜因为成大疫情的关系，我们大家没办法到现场来，就跟我们一起就是来做切磋研讨，但仍不会阻止我们就是有这个热心可以进行线上的交流。好，所以今天待会我的演讲就是刚刚陈老师介绍这个题目 self-testing of steerable quantum assemblages。那我的演讲待会就是会用英文来进行。那如果各位同学有问题的话，那我看能不能线上演讲中断都问我问题都没关系。好。那就随时有问题的话可以发问这样子。Okay, so today what I'm going to talk about is self-testing of steerable quantum assemblages. And then before my talk, so I would like to thank Professor Shin-Liang Chen for giving me a chance to share my work with you. So if any of you have interested in our work, you can take a reference of this article which was published last year on quantum. And also, I would like to thank my collaborators, including Huan Yu, Wenbin, Jody, and Yuanan, for contributing in this work. So here's my outline today. So first of all, I will like to share that the idea of quantum steering. And then after that, I will tell you some brief idea of device independent certification of steerable assemblages. So finally, I would like to share our main research, which is self-testing of steerable assemblages. Okay, so let me start by introducing this self-testing quantum steering by this very typical entanglement-based quantum key distribution scenario as an example. So here we consider there is a pair of entangled particles, which is in the maximally entangled 2 qubit states. And the first particle is sent to Alice, and while the other particle is sent to Bob. So during each round of experiment, then Alice can perform some measurements to measure her particle. And on the other hand, what Bob does is just to observe the state he receives. And then, after measurement, Alice can obtain also one of 2 outcomes labeled by +1 and -1. So after this kind of experiment, many rounds, so actually Alice can perform one of 2 measurements, for instance in X basis or in Z basis. And what Bob obtains finally will be in the states of +, -0, or 1, this one of 4 states. So after repeating this kind of experiment many rounds, then they can write down some kind of this data table. And the first column represents the Alice inputs of Alice choice of measurements, for instance X or Z. And the second column represents the measurement outcomes of Alice, here labeled by +1 and -1. So finally, as we say that Bob's task is just to observe the states he receives. So this can be written down as +, -0, and 1. So because Alice's job is just to, so here we just focus on which kind of measurements she performs. just is in the x basis or z basis. So actually she can just write down 1 or 2 as the measurement basis. So generally, Alice can just use this symbol A to represent the measurement inputs. And here, she can just write down this X for generally represent the, her outcomes measurements. So by using these kind of symbols, then Bob can write down the states he receives as this states row condition on A and X. So this row X, the set of these states, we will call this kind of observable as an assemblage. And this quantity is very important in this scenario of quantum steering, and also very important in the rest of our work. So in this example, an assemblage represents the set of plus, minus, 0, and 1, the set of these 4 states. Okay, so a natural correlation is that so okay, we can represent this this kind of measurements as this simple plot to represent this kind of quantum steering scenario. And the question arises is that if there's no entanglement, okay, so because previously we obtained this plus, minus, 0, and 1 because we assume that the state shared between S and Bob is in a maximally topography entangled state. So if there's no entanglement, and can Alice still remotely prepare these states on Bob's side? So this is a very natural correlation. So because there's no entanglement resource, so here we have to only consider a classical strategy. And as a result, the best way that classical strategy can do is we can mention that there's a classical computers. And during each round of experiment, then this computer creates some real numbers. For instance, I will just label by them as 1, 2, 3, and so on. So for instance, in this each round of experiment, maybe this time, this computer create the number 3. Then this 3 is encoded in a particle and sent to Alice. So Alice obtains her measurement outcomes according to this number 3 and her measurement choice, X. And also this number is encoded in another particle. So this particle just labeled by sigma. This states and they're according on this number 3, this classical numbers. So if Bob does not know what Alice's measurement choice, X and A, then what he receives is just the state sigma lambda. But if he knows the information about A and X, maybe Alice just send this information to Bob, then he can update his states from sigma lambda to rho X. And just by, so mathematically, it just can be written down by this equation. So this is nothing but just a convex combination of the state sigma lambda. So here's very simple, just by doing some convex combination of this sigma lambda, then one can obtain the final updated state. And because in the quantum information scenario, what we focus on is a probability distribution. So this kind of coefficient can then be written, represented by the probability of lambda and the probability of the measurement outcome A according on X and lambda. So this final form is the best way or the best classical strategy that Alice can prepare for Bob. And we call it as a local hidden state model. And it was first proposed by Weissman, Jones, and Doherty in 2007. And then in 2012, this group of people, they find out that this kind of strategy is useless in the quantum key distribution scenario. So in the previous slides, we showed that if Alice and Bob share maximum entangled states, then the state obtained by Bob, this 0, 1, minus, and plus, is very useful in quantum key distribution scenario. But in this classical strategy, the state prepared by Alice is useless in a quantum key distribution scenario. So we know that what we're interested in finally will be assemblages which cannot be written in the local hidden state model. So consider, or we can imagine that this is a space of assemblage. And the classical strategy, or the local hidden state model, actually they form a convex set, or we can just imagine that they form a circular shape. And outside this set is the assemblage we are interested in. And this set, or in this yellow color, is called a steerable assemblages, because we use this term is that Alice can somehow remotely steer bubble states. So this is what this steering comes from. And also, people are interested in this set because it sufficiently verifies the presence of entanglement. And secondly, it sufficiently and necessarily verifies the presence of non-commuting observables of Alice. And third, it outperforms the set of local hidden assemblages. So the third part, in some sense, is that there always exists a quantum information task that this set any state from this set can outperform the probability of the probability of this any point of this set can always outperform that any local hidden state assemblages. And finally, this steerable assemblage can use for verifying random numbers. Okay, so now we know that steering is a very useful resource. So naturally, it's very important to verify steerable quantum assemblages. And a strategy for way is that we can perform quantum state topography to see if this assemblage admits this local hidden state model. So the idea is that we perform many rounds of this experiment, then we can eventually know what the state it looks like, and to analyze if this state admits this mathematical form. So a flaw of this method is that it takes too much resource, and the number of required measurements is proportional to d or power of 2n. Okay, so here I explain it as Chinese for convenience. 好，所以各位同学就是说，这些是我们做这个量子的这个断层扫描，就好像我们就是在身体检查的时候呢，要送一个人进去，就是做这个 MRI 的断层扫描。那这个机器呢，可以从非常多的角度去帮这个病人去做照相，那可以看到他的体内大概长怎么样子。所以从这种各种不同的角度去拍摄下来呢，那这是需要花费非常多的资源的。所以我们做量子断层扫描的概念就有点类似像这样子。那它会花费了非常多的量子资源在上面。Okay, so another sufficient way is called steering weaknesses. So the idea behind this steering weakness is that we just perform some measurements on some observables, here labeled by omega AX, and then we check the expectation value of the summation of all these expectation values. Then if the expectation value is above the number alpha, which is proof that it can never be existed by a local hidden state model, then we can judge that the assemblage is steerable. And otherwise, we are not sure what is happening. So from the experimentalist point of view, this one just to have something like a yes/no result. So an experiment just to check if the expectation value is above this alpha. If it is the case, then they will say, okay, so yes, the underlying state or underlying assemblage is steerable. And if this is another result, then we don't know what is happening on this assemblage. So, and the advantage is that only a few of observables are required. And it's not, one does not need to have so much measurements to perform. And here we can understand this steering witness from another point of view. Here is the space of the assemblages, and this circle represents that the set of locally dense assemblages. And outside this set, there's a point, there's an assemblage, which is the assemblage we would like to verify. And also this omega x observable we perform also place a rule in this space. Here represents a line here, or sometimes we call it as a hyperplane. So one just have to find the line that separates this point and this local density set. So from a very simple mathematical idea, we know that any point on this line should give us the expectation value equal to alpha. And the left-hand side, including all these local density assemblages, should give us the alpha, give us the expectation value which is lower than alpha. So this means that once we obtain an expectation value greater than alpha, then we can judge that the state or the assemblage is steerable. Okay, so but in the real situation, it is not so perfect. Sometimes we often meet the situation that this omega x is not so perfect in this line, but sometimes it's in another line here, and we don't know this situation. So in this situation, this omega prime x, and sometimes we have a bad luck that it also crosses the section of this local density assemblage. So this means that the expectation value is lower than alpha. This situation is not hold for all local density assemblage, but some local density assemblage. Then this means that even we obtain a value greater than alpha, then this assemblage sometimes is also in this local density model, and we cannot judge that it is steerable. So to deal with this situation, we need some powerful tool. And before proceeding on, here I would like to give a metaphor for steering witness. So to witness quantum steering, the first way is to perform quantum state topography. And here we call it as a full reconstruction. So a metaphor for this is that we can imagine that there's an elephant in front of us. And on our hand, we have a camera, and we are in a very dark room, so we cannot see this elephant from our eyes directly. So we can take several pictures from many angles of this animal. Then eventually, from the picture, we know that, oh, the animal in front of us is actually an elephant. And the idea of steering witness, or sometimes we call it partial reconstruction, is that if the only information we want to know is which kind of animal is in front of us, then actually we will just have to take partial pictures of this animal. And from here, we can also know that the animal in front of us is an elephant. Okay, so no matter which kind of this method, then here we make assumption that the measurement devices are perfect. And in many situations, it is not the case. It's that sometimes we cannot control the device on our hands. And then this means that we cannot fully characterize the observables that we measure in the laboratory. And in this metaphor, it means that this camera may be hacked by a third party. And for instance, even if the animal in front of us is an elephant, but the final picture we see is a mouse. Okay, so in this situation, we call that the measurement devices are imperfect. So we need a useful power called device-independent quantum certification to deal with this situation. Okay, so here is a brief summary of device-independent quantum certification. So here I will not give you how the physical concept behind it, but just how do we operate this device-independent certification scenario. So to operate this, that we can imagine that during each round of experiment, there is a pair of particles sent to Alice and Bob, and we don't know what the state looks like, so it is drawing a black box. And during each round, Alice can perform one of two measurements labeled by X, and she can obtain one of two outcomes labeled by +1 and -1. And we use this A to represent her outcomes. And similarly for Bob's side, as B and Y. So after repeating this kind of experiment many rounds, then they can obtain this kind of a data table. So the first two represent for A's information, and the third and fourth represent Bob's information. So, and then an important quantity is that this AX and BY, which represent the expectation value of A times B when the inputs are X and Y. So here, as an example, this A1, B1 represent the probability A equals to B minus probability that A is not equal to B. So in this example, this quantity is 0. So next important idea is these inequalities, which list A1, B1 plus A1, B2 plus A2, B1 minus A2, B2, which is lower upper bounded by the value of 2. And this quantity, or this inequality, is called a Bell inequality, which was proposed by John Bell in 1964. And we also call this inequality as a CHSH inequality, because this inequality was proposed by these 4 researchers in 1969. And today, I will not talk about the idea behind it, but I will just show you that how to use inequality to verify quantum steering. So in 2007, Weissman, Jones, and Doherty, they showed that this inequality should obey for all local coherence assemblage. So this means that once we obtain the value is violated, then we can judge that the underlying assemblage must be steerable. Or otherwise, we are not sure what is happening on these assemblages. So as you can see, this is also a yes/no question. And then this, so sometimes we also call that the black box quantum certification. This inequality is also device independent steering witnesses. And the benefit for this witness is that no assumption is made on the preparation or the measurement devices. So this means that we don't have to assume that what the observable we are measuring, or we don't have to make assumption that what the state is preparing. So there are other applications for this device independent certification, including entanglement certification, randomness certification, and incompatibility certification. And an extreme case is that it can even use for certifying of quantum state itself. So an example is that if we obtain the maximum evaluation of the Bell inequality or the CHSH inequality, we can judge that their shared state is the maximally entangled 2-qubit states up to some local unitaries. So this statement, we call it as a self-testing. Okay, so mathematically, the definition of self-testing of quantum states is that we say this correlation self-test the reference states. So here, the correlation in the last page is the maximal violation of the CHS inequality. And the reference states in our previous example is the maximally 2-qubit entangled states. Okay, so if for any underlying states compatible with the correlation we observe, there always exists a unitary for Alice and Bob, and some insular and junk states, such that this inequality holds. This equality holds. So to to explain this more simply, we can see it from this plot. So where that the underlying state psi is what we have in the laboratory. And this insular is just a mathematical production. So what we have in our laboratory is just this column states. So if mathematically there exists an insular and a unitary for Alice and Bob, such that they perform some rotation on their system, then the insular will become the reference state. And other systems are just collected at some junk states, which is not very important in this scenario. Okay, so now actually this unitary insular junk state, they can be collected as together, and then we can simplify this. We can simplify this definition more simply, that we can just do find out the complete positive and preserving map for Alice and Bob, such that after the map of the underlying states, then it becomes the reference states. So this definition will be simpler. So the goal of self-testing is to construct the mathematical form of lambda A and lambda B. If we can find out the existence of this CPTP map, then we can self-test our state. So the first way is the analytical method, which is divided into two sub-methods. And the first one is the typical method proposed by Mayer and Yao in 2004, and then modified by Mogao, Yang, and Scaroni in 2012. And the other one is called the operator inequality method, which was proposed by Kaniewski in 2016. So this analytical method has a benefit that is universal. So in the sense that it can principle to generalize to arbitrary dimension and number of parties systems. And the second one is the numerical method, which is also can be divided into two approaches. The first approach is called the swap method, proposed by Yang, Vertesi, Benko, Scaroni, and Navasquez in 2014. And the second method is what we call the CPTP method, and it was proposed by our work last year, which was introduced in my very early slide. And a benefit for this method is that it is robust. So in the sense that even if there is a large noise in the systems, we can still judge that what's the distance between the underlying states to the reference states. So because in the previous page we have self-testing of quantum states, and in our work we can generalize the self-testing to from the states to the assemblages. And then so actually the idea is very similar, that we say that this correlation self-test the reference assemblage. If for any assemblage compatible with our correlations, there always exists a CPT map lambda. Then after this map applying on our underlying assemblage, it can transform to the reference assemblage. So to introduce how this method works, I use self-testing of the CHSH type assemblage as an example. So the CHSH type assemblage is the plus, minus, 0, and 1, these 4 states, which I also introduced a very early slide that is very useful in the QKD scenario. And this assemblage called the CHSH type assemblage is because if we apply some proper measurements on these 4 states, then the CHSH inequality will achieve the maximal quantum violation. So we can see this more clearly from this plot. So if Bob performed the measurements on these 4 states, then they can obtain the maximal violation of the CHSH inequality. So our equation is our self-test equation is in reverse way. That if we obtain the maximal violation of the CHSH inequality, can we still judge that the states received by Bob is 0, 1, plus and minus? So this is what we want to ask. Okay, so the answer is yes. And then here I just maybe take some few minutes to introduce how the procedure works. So first, from this Choi-Minkowski isomorphism, we can transform of the problem that finding this CPTP map to a problem of finding the existence of this Choi matrix omega. So this lambda is the CPTP map, and the omega here is the positive semi-definite operators. So they have this kind of if and only if properties. And secondly, we assume that we are in a perfect case, which means that the underlying assemblage is equal to the reference assemblage, is equal to 0, 1, plus and minus. And we will drop this assumption later because we are in a device independent scenario. And then, because they are equal, this means that the identity, that the lambda here is the identity operators. And if the lambda is the identity operator, then the corresponding CG matrix is the maximally entangled state. Then from a very simple mathematics, we can rewritten this omega as this something looks like this way. So B1 is poly Z operators, and B2 is the poly X operator. And then we can just represent these 4 operators as O, 0, 0, O, 0, 1, O, 1, 0, and O, 1, 1. And eventually, we can represent these operators. Just write down the trace of this Oj and sum overall together. Then we define the fidelity between the reference states, the reference 0, 1, plus and minus these 4 states, and then this assemblages. And we define the fidelity because fidelity is equal to 1 if and only if the reference assemblage is equal to the assemblage after the map. And if they are the same, then we have a perfect self-testing. So finally, if we take fidelity between these 2 operators, then this Ij will be cancelled, and left just some coefficient between each trace or Ij. So finally, what we have to do is to minimize this polynomial of these terms. And then we drop the assumption that rho x and by. Namely, we drop the assumption that they are equal, and we drop the assumption that B1 is equal to poly Z and B2 is equal to poly X. We only assume that assemblage is a quantum assemblage, and the operator are quantum observables. Okay, so the final problem will be that we minimize the polynomial of this quantity such that, okay, under the conditions or under the constraints that the CHS equality is achieved the maximally quantum violation, and the other constraint is that this correlation is admits a quantum theory because we are in a quantum world. And this mathematical problem can be solved by a tool called assemblage moment matrix, which was proposed by me, Constantino, Yong Chen, and Yuan Nan in 2016. So from here, we can actually, in principle, solve this problem. And we further consider a general situation that if a violation of the CHS inequality does not achieve the maximal value, which we call the robust self-testing, then the problem becomes also similar, that we minimize the polynomial of these terms under the constraint that the CHS inequality is a little departures from maximal quantum violation. And also, this correlation should admit a quantum theory. So basically, these two problems are similar, but in a robust scenario, we can even consider that the violation does not achieve the maximal quantum violation. So I just show you our numerical results. And here, this x-axis represents the value of the CHSH inequality, and the y-axis represents the fidelity, the low bound of the fidelity between the underlying assemblage and the reference assemblage. And this dashed line represents that the best classical strategy that can achieve. So as we can see, the maximum violation to square root of 2 is around 2.82, and we obtain the low bound on the fidelity is equal to 1. So this means that if we obtain the maximum violation of the CHSH inequality, then we can judge that the underlying assemblage must be in the state of 0, 1, plus and minus. And even if the violation does not achieve the maximum violation, for example, from 2.6, between the 2.6 and 2.8, then there's some still fidelity, or non-trivial fidelity we can judge. And of course, there are other kinds of assemblage, which is also interesting, but I'm not putting this result on our slide here today. And if you have any question, you can also take a look of our work. So finally, I will share 3 take-home messages with you. First, steering is a useful resource, so it's important to certify the presence of steerability. And second, when the measurement devices involved cannot be fully characterized, we use device-independent quantification. And finally, we can even use device-independent quantification to identify the exact form of the assemblages. And with that, I would like to thank you for your attention.
So thank you, Shin-Liang, for the nice talk. So I have a question here. So, so can we do some test on the IBM Q machine? You know, if we, you know, in this IBM machine, the maximally entangled state generates not always perfect. Can we somehow run this kind of the self-testing on this crowded machine?
Okay, I think basically it can always works on the so-called IBM platform, because if the platform allows us to, so if the platform allows us to construct these systems, for instance, in the most simplest scenario, we have 3 parties, and one create quantum states, and the other 2 they try to measure the systems. And if we can measure the system in 2 bases, X and Z, and obtain these binary outcomes, so actually this is a very simple Bayes scenario that all we have to do is to judge, to see if this inequality, this CHS inequality, if they obtain, if this CHS inequality achieve the maximum quantum violation. So if we can achieve the maximum violation, then we check if these four states also in the 0, 1, plus and minus. Then we can compare these two results. And then we can maybe also draw a plot for this fidelity estimation. And to compare fidelity experimentally with the theoretical result, then I think it can be done.
So I see. Okay, thank you.
You're welcome.
Okay, so I think it's time for the end. So if you have any question, you can send an email to Shin-Liang. So he would be loved to answer your question. Okay.
Okay.
So thank you, Shin-Liang.
Well, thank you for inviting me.